it automatically parses the files. We can actually look at these. We can actually look at these ground control points. And one thing we haven't done yet is to use the pick, and that's a good place to use that. There's something here where you can just look at a part of the input, not the whole file, with the viewer. So we say here, click input, and then again you have this cursor, and I'm selecting an area here. Maybe like this. And if I now say view, it has several new options. It has this inside, and that basically will clip the points to that particular area that's inside this rectangle. These are 4 coordinates defining a rectangle: x min, y min, x max, y max. And then it also will try to visualize the control points. So if we press start, let's see what happens. We get only the area we selected, and if you see there are these balls, these red balls in space. These are the control points. Control, you can zoom in and out. Control, zoom in and out. Holding down control and holding down alt, you can pan. And there you see the control points, how they are lying in the surface. Now I press T to triangulate the points, and I press minus to make the points go away. And now I very nicely see the control point lying in the surface. Again, with control, I'm zooming in, and then I I can see that half the control point is above and half the control point is below the surface. And that's the best case scenario. That means, I have just the control point that was measured by the surveyor exactly aligns my LiDAR. So that looks really good. Both for this one and also for the one in the behind. But I seem to remember that somewhere there was a point also before I triangulated. So I'm zooming in here a little bit. But I can't see it now. So I'm changing the shading, that was H, shading, by pressing H 3 times. Because in the wireframe, I can look through. And somewhere there I see a control point. There it's somewhere. In the middle of the forest, there's a control point. So it looks like there it is, getting closer. So it looks like the forester went in the middle of the forest, the surveyor, to get a control point there. I press escape to get out of the viewer, and now I will do a control point calculation. Now it's important to, you see this is still enabled, and if you do any operation now, all operations will only operate on this part. So it's important to disable this if you want to work on all the data. Disable. Also, our data is completely raw. It is not classified. And there is is the option of running only on the classified data, but it's not classified yet, it's raw data. We're going to do the classification in the next steps. So I need to uncheck this because I will, otherwise the filters will filter away every point because there's no point with class 2 and there's no point with class 8. So I'm removing these checkboxes. And the output file, let's give it an output name. Let's call it control.csv. And then I'm running, and the list of files. Control point file is the input, cps.csv, and this is an interesting thing here. What does this mean? Parse sxyz. Any idea what this could mean? Parse sxyz. This has something to do with this file. I need to tell LAStools the control points are the most important part about the control point are the 3 coordinates x, y, and z. I need to tell LAStools in that file here. It's not a LAS file. It's a comma-separated value. It's like an Excel spreadsheet file. Where is x? Where is y? And where is z? In which column? And that is what this does. X is in column number 2, y is in column number 3, and z is in column number 4. And what does the S mean? S means skip. So it means skip x, y, z. So skip the first column, and then the next 3 columns are x, y, and z. If you don't do this, then it will fail because in the first column it says things like open area, field, forest. There's a description of the control points that's only meaningful to human groups and not to LAStools. Okay? We'll look at this file later and then you see these outputs. So I say start. What's going to happen now is that LAStools will take all the points that are in close proximity to the control points, maybe 5 by 5 meters around it. It will create a triangulation, and it will then compare the control point elevation to the LiDAR elevation by looking in the triangulation for that value there. And then it will calculate the difference. And that difference is supposed to be as close to 0 as possible. Okay. It's done. So it reported some root mean square error and so on. Some standard deviations. Let's look at maybe first let's look at the original control point file, which for me will open up in OpenOffice, the cps.csv. So that is in that file. The first column is the type of control point, and then easting, northing, z. So that's like x, y, z. And these are the points measured by the surveyor. These are expensive points usually, but they are a very crucial part of a LiDAR campaign. It's kind of cool to have these airplanes flying around collecting all these points, but the ground troops that go in and measure these points the old way. They are really crucial because they are the only way you can know that these fancy points from a plane are actually correct. So you can't have one without the other. And these describe what the points are. Open paved, that's likely on the runway. Field, that's the grass area that's next to the runway. And then further down there's something where it says forest, I think. Oh yeah, forested. Those are the ones hiding under the tree. Okay. Now let's look at the output we generated. It should be in the quality directory. Oh no, it's not the quality directory because we didn't specify the quality directory. It is in, when you don't specify anything, and that happens to me regularly, then it is in the bin directory, I think. It is where you start with the tool. Yeah, that is. So now I'm just copying and pasting it. I'm just dragging and dropping it into the quality directory. So it's in the right place. So yeah, whenever you don't know where the output went, it's a good idea to check in the bin directory or check in the directory where the raw LiDAR file was. These are the two most likely locations where you will find the output. So I found it, and now I'm opening it up quickly. That's just in the file. It's really just a text file with commas separated. And before I had type easting mousing Z, and what LAStools has done, it has added two more columns. It has added them in the front. The column is called diff and LiDAR Z. So the LiDAR Z is the second one, and it's just the elevation that was calculated from the LiDAR data at the same location where the control point was. Here's the control point elevation. Here's the LiDAR elevation. And the first number is just the difference between the two. And that difference is hopefully very small. And yeah, it's 14 centimeter, 2 centimeter, 5 centimeter, 7 centimeter, 16 centimeter. Looks all pretty good. until you come a little further down. 26 meters, 17 meters. Oops. What happened here? Well, remember we looked at the control points already. Some were hiding under the forest, and it says here, forested. We used all points, all of them, not just the ground points, because we didn't classify yet. So many of these points are now landing on top of trees, the LiDAR points. But the ground control point is always from the ground. So when we don't have classified data, we must not look at the forest points because they make no sense. Because we're using all the points from the top of the tree and from the middle of the tree and from the bottom of the tree and from the ground. So the likelihood that our ground control points in the LiDAR is close to a ground point is very small. It would have to be an opening in the forest. Hence, it's not surprising that in the forest, these values are very big. We must not use them. We must only use them after we do ground classification and then run it only on the ground points, the quality check, and then you can do it. Then you can look at these. Either way, we can always expect in the forest to be higher errors because the LiDAR will not reach the ground as often, and often there are also a bit more errors in figuring out what's ground. Because I mean, walk through forest, there's all kind of ferns on the ground and little shrubberies, and it's difficult to decide what's really the ground and what's just above the ground. So, in general, a nice asphalt surface gives much better ground accuracy than in the forest. But at the same time, usually it also doesn't matter that much in the forest because, you know, you're in the forest. The water has, I mean, whatever you do in the forest, it tends to be less accuracy demanding than if you want to compute something that's on the highway. Okay. So now we did a ground point check with last control. Now let's do some density checks. We have a certain density requirement for our data. We know we want at least a certain number of points per square meter. Let me quickly look at my cheat sheet here. Yeah. So let's say, for example, we wanted a 5 points per meter density. That's what we were hoping to get. So the tool to check density in more detail is called LAStGrid because it's on computed density raster. So I'm looking for LAStGrid. Again, I'm loading all the scripts. I'll merge them all into one, and I call the output. I call the output density 5 pt 5 ps dot png. So I'm creating another image. Oh, whatever. Density 05. Yeah. Again, I choose the output directory to be the quality directory. So now, I want to compute density. So the item item is not elevation. The item is now density. And I want to create a coloring of the density. So I use color options, and I use false colors. And I have a very good idea how I want these false colors to be. In this case, I'm using a step size of 1 meter. So 1 meter by 1 meter, I want to have 5 points in every 1 by 1 meter on average. So I say, well, 5 points I want to have. That should be the color red. My color ramps are always from blue to red. So if it's blue, it's significantly lower than 5. You could put a different number there, if you wanted to show me the areas which have only 3 points. This is really a choice how you want to visualize it. I'll just go the entire range right now. If it's above 5, it will be just clamped down to 5. And the output format should be a PNG again. And we also want to specify the projection. So we don't forget that again. UTM 19. You see, it's kind of annoying when the projection isn't in the file, you have to specify it all the time. So it's nice to put it in the file. So let's have a look at this command line and again translate it into English. We're running LAStGrid on all the files and they will get merged. We're computing the density, meaning we're counting how many points fall into every cell. We don't specify the cell size here because the default cell size that will get used is 1. If you don't say it, it's going to use 1. We use a false coloring, and the false coloring should be blue if the value is 5, and it should be red if the value 0, and the red if the value is 5. The output should go into the quality directory. It should be called density 05, and it should be in the UTM zone to make a KML file. Okay, hit run and go. And afterwards we're going to do the exact same thing again with a slightly different color ramp to compute a different density. And which visualization you choose, which colors you map, that is the choice that the person designing the quality check has to make. Like I just chose 0 to 5. 0 meaning, well, obviously very bad. But I could have chosen 3 to 5 because 5 is what I'm interested in. 3 is already bad. It would make it more drastic, the effect of badness. Because it would already 3 would be blue in the visualization. Okay, the first one is done, so let's do the second one right away. I specify an output file name. This time I call it density 10 because I don't want to get too many points either. If I tell the vendor give me 5 points per square meter, I don't want to get 30 points per square meter because that could just be slowing down my processing pipes too much. I just want 5. Or so I'm changing the color options now. This time I go from, I visualize everything that's between 5 and 10. So 5 will be blue and 10 will be red. And I want 5. And if it's a bit more than 5, it's okay, but it shouldn't all be 10, it shouldn't all be red. for this fake quality criteria I'm making up right now. Okay. And again, let's explain using the command line. I say run. The beginning is exactly the same. The difference starts here. I now look at the different color ramps. I color it 5 is blue and 10 will be red. And I should give it a different name, and I did. Yes, I call it density 10, because that visualizes density up to 10 points per square meter. Okay, starting that. What time is lunch? At 12. Oh man, we're so behind. We're so behind in time. People have so much to do. Can we skip lunch? I think they all want to skip lunch. You need the energy. This basically concludes the quality check so far. But let's first look at the results. Mine are already in. I have now these density grids. I have KML files for them. If you don't have KML files, or if you don't have Google Earth, you can just directly open the image file. I should have maybe said that a little earlier. So, voila, here's my 5 points per square meter. So I hope 5 points wasn't the desired, remember it was, I think it was, the average was 3 points per square meter we saw in the last intro reports for one slide line. So that's roughly the colors you get here, that's about 3 points per square meter. Oh, one thing I actually completely forgot. Oh, stupid me. It's in the PDF. Okay, I forgot it in this step. It was a test and nobody said anything. I made the density now of all the points. But I said before, we don't want to do it of all the points. We only want to do it of the last returns. So I should have added a filter, right? Last only, minus last only. That has been missing. But I'm not going to make you do it again. Because now you will, I was wondering, why do I see some structures in here, you know? You shouldn't be seeing structures like trees in your density grids. I mean, they should show that a little bit maybe because they move the points around, but they shouldn't increase the density. So if trees increase the density of your density grids, then your density grids aren't very useful for visualization, because they're containing information about how much stuff is on the ground, and that's usually not what you want for a density check. So let's just look at the last one, and then this is the other one, the one that went from 5. Now 5 is blue, 5 or lower. So the blue areas are not all 5. Remember, we saw some that were only 3 because that's what last info told us. On average, it's like 3 points per square meter. Now, last info tells you an average over the entire file, but that could mean, you know, I have super high density here, and then it tapers off to here. In these images, you see the density distribution. So now I see here, sort of, I can see hot spots, and I can also see wherever I have trees, I get very high densities, and that's because I count all the points from the trees, which I should not have done. I forgot the option last only. If you go through the first tutorial, which is called LiDAR quality checking, it goes through all these steps again, but there I think I did not forget minus last only. So there you have it. And now it's lunchtime, so I'm going to show you all could need a break now. I'll see you after lunch. lunch, we will use that same data set